All right, this is going to be practice problems for the torsion problem set, and we're going to do the last one in the set at the moment, which is problem 923, the 2019 exam question number 2. So this is one of those mega beam problems that incorporates all the different deformations that we have and looks at displacement due to possibly axial things, shear, flexure, and torsion all in one go. So the beam is made of a material with this stiffness and this Poisson's ratio, and it has opposite corners located at 0, 0, 0 and 5, 10, 100 centimeters. So it's really long in Z compared to the other dimensions, and it's fixed on its Z equals 0 surface and otherwise free, except for an applied stress of this on the and this. So this is the stress on Z in X. It's a shear stress applied and an axial stress applied on Z in Z, both on its Z equals 100 centimeters surface. So Z equals LZ surface. And the first thing we're going to do is show that this is equivalent to a total force on that surface of this and a total torque about the centroid of that surface of this. So that's kind of a nice thing to start a question with, because it means that even if people get part A wrong, they can't prove this, like they're not sure how to do that, then still they'll have the force and the torque at the end to be able to do part B, where you need that stuff to do it in Maple, and they have the stresses applied already, so they can jump right into part C and do that stuff in FlexPDE. So let's start off the first part of this by saying that we're going to enter the material parameters. E is 200E9, nu is 0.3, and we've got the lengths of this. Lx is 5e minus 2, so 0.05. Ly is 0.1, and Lz is 1. Now we can enter these stress distributions. Szx is equal to 30E6 times y minus 0.05 meters over 0.05, and Sz is equal to 30E6 times, let's see, x plus y minus 0.05 all over 0.05. Okay, now we're going to figure out what the total force that's created by this is, and we can find that by just integrating these stresses over that surface. So we'll say the force in Z would be equal to the integral of Sz, the stress in the direction of Z, integral of Sz over that surface. So we're going to integrate twice, integrate from y equals 0 to Ly, and from x equals 0 to Lx, and that should give us the force in Z. And it is 75 kilonewtons. What about the force in x and the force in y? Force in x we could get by taking the integral over the surface of what? Of Szx, the stress on the Z surface in the x direction. And that is 0. This produces no net force in x as expected. And what about the stress in y? Fy on that surface would be the same integral of the stress on the Z surface in the y direction, which is 0. We don't have any S on Z and Y. So we'll just put that in. And there we go. So we have indeed a force of 75 kilonewtons in the Z direction and no force in X or Y. How about the torque? To find the torque that is produced by a stress distribution, we will be taking some integrals of little bits of torque that's produced at each different point. So to find the torque about X on this surface, how would we get a torque about X on this surface? We're not going to get anything from a shear stress on this surface, so nothing from Szx. Maybe we should draw out this surface actually. This is not quite the directions that we need. What we need is X going to the right and Y going up. Very, very amazing, I know. So what do we have? How can we get a moment about X? a torque about x at a point on the surface? Well, we could only get that if we have a displacement away from the x-axis and a stress coming out of the page. So from the y coordinate relative to the center times the stress in z, which would be out of the page, that will be giving us the torque about x. So that means we will say torque in the x direction will be equal to the integral of, so it's always going to be one of these, an integral of something, but what are we integrating? We're going to be integrating this time the y position relative to the centroid times sz, the stress in the z direction. Now what's y bar? We can put that in, we could do the averages, but it's obvious in this case that it's just because it's a rectangle, it's halfway there. So y bar is equal to ly over 2. And I mean, it's obvious only if you think about it. Maybe it's obvious if you don't think about it. But because this is a rectangle, the average y position, this together is a rectangle, the average y position is just going to be, if it goes from 0 to ly over 2. And lx, the average x position from 0 to lx, is going to be lx over 2. Okay, so y bar is that. X bar is lx over 2. Yeah. So then, torque about x is the integral, we're going to add up all the little bits of y position relative to the centroid times the force out of the page, which is the stress in the z direction after we integrate. And this should give us what was stated in the question, which was 2,500. Okay. Next, we are going to be finding the torque about y. Similarly, if we go back to our diagram here, to find the torque about this one, it'll be the negative x position times the stress out of the page will create a positive torque in the y direction. So for this one, we'll take the same integral, except we'll be integrating negative the x position, x minus x bar times sz over the same surface. And we find negative 625, which I believe was also what we were supposed to get. Yep. And then the last one is going to be, how do we find the torque about z for this? Let's get the picture back again. Maybe I can just copy this in so we don't have to jump around as much. Yeah. So there we go. Very helpful picture. Torque about z is going to be depending on shear stresses. So this is something that we worked out in the notes as well, but we can just rethink how it works. We're going to have a stress on z in the y direction times the x displacement will give us a positive torque. So that will be the y displacement, y minus y bar, times the stress on z in the, oh wait, I read that wrong. The x displacement times the y stress. So x minus x bar times szy. And then we're going to be getting another one from the x stress. This is going to produce one at a y, depending on its y position, in the other direction. So we'll take minus y bar times sz in x. Yes. And this should therefore be producing the net torque in the z direction. And do we get minus 2,500? Yes, we do. So there's the proof. We've done it. We showed that this stress produces a net force of 0, 0, and 7,500, and a net torque about the centroid of that surface of 2,500, negative 625, and negative 2,500. Next part is taking the z equals 0 surface to be fixed and using Maple to find the y displacement only, not the x and z displacement of the far corner point, which is at this point. And a hint is to treat the torque about the centroid as an applied moment to the surface and the net force as an applied force. Normally we'd need the internal force and moment to do this. In this case, though, we've already got it. Because the force is only in the z direction, we're not going to be having any change in the moment as we go along this beam on this cross-section, right? The cross-section is just going to have this every time because the x and y components of the force, the shear forces on this z surface, are just 0. So we already have the internal force and moment in the beam all the way along. Now, where can we get y displacement from? We could get y displacement from the Poisson's ratio through the axial stress, and that would be maybe epsilon y at the end would be equal to fz applied at the end divided by the area. So let's work out what the area is. Area is equal to Lx times Ly. And this will be the strain at the end. Actually, not quite. This is the stress at the end. And we'll take that stress and divide it by the Young's modulus. And that'll be the strain at the end. But this is the axial strain. So how do we get the axial strain in the y direction? Really, this is axial strain in z. This is going to couple to an axial strain in y by multiplying through the Poisson's ratio. So negative Poisson's ratio times this stress divided by E will tell us the coupling from the z-axis into the y-axis in axial strain. Now, if we want to turn this into a displacement, V tip, maybe we'll call this V Poisson from the Poisson coupling at the tip, we will have epsilon y tip times the distance from the center. So the center is on average going to hold still if we've got that z equals 0 surface anchored, and the center of the z equals Lz surface is going to be a distance Ly minus y bar away. So if we take that strain that we worked out and we multiply it by the length, we'll have the change in position. The distance, so we multiplied it by the distance from where it's going to hold still. All right, how much does that move? Not very much, about 1 micron. What else leads to displacement at the tip? Well, we've got a, so in the y direction, it would be the x moment. The x-directed moment will lead to a curvature in the negative y direction. So the curvature in y is going to be equal to negative moment that we found in x. So really this is what we call torque in x. This ends up being the same as the internal moment all the way along. Negative tx divided by EI. And we have to work out the EI for bending in the y direction. Really, we call this EIY. So EIY is equal to what? E times the thickness in y, Ly cubed, times the thickness in x over 12. So that's the flexural rigidity. And the curvature, which is going to be constant all the way along the thing. So that lets us pretty easily integrate it twice and figure out what the flexure tip is at this surface. Integral of cy twice, but when we integrate it twice with respect to z, we're just going to be multiplying it by z squared over 2. So this will be cy times Lz squared over 2 after we substitute in. So there's the displacement at the tip from flexure. It is 1.5 millimeters in the negative direction. So the Poisson displacement was so negligible, not surprising since this beam is much longer than it is thick. We have no shear force, so the shear displacement at the tip is going to be 0, but we do have a twisting moment. We have a moment in the z direction on this z surface, and that's going to lead to a torsional strain. How do we work that out? Well, we have a constant moment in z applied, tau z, or tz, torque z here. And this thing, after we, let's see, we divide that by JTG, similar to dividing the moment by EI, and this is going to give us the torsional strain, which is the angle per step in Z. So the total angle, theta tip, because this thing is going to be a constant this time, all we have to do is multiply that by Lz, and that will be the theta angle that the tip bends through. So we're going to need to put in what JT is. And this is something we actually didn't do in the notes, which is work out for a rectangular cross-section what the torsion constant was. So let's see then. We're going to go back to our notes. Up near the top, we had this table of torsion constants, and let's make sure that we're using this correctly. A and B are half of the long and short side lengths. So that means JT for this rectangle should be lambda times half the long length. What's the long length? It would be Ly. Ly over 2 times half the short length, Lx over 2, cubed. And what is lambda? This is the long side over the short side, which is 2. So it's going to be 3.664. Okay, and this is from table in section 9.1. All right. We also need to work out what G is. G is E over 2 times 1 plus nu. Now this angle, this twisting angle, is going to lead to y displacement after we multiply it by the position in x. This is using a small angle approximation that we worked out. So we can say V torsion tip at that point is equal to theta tip times Lx over 2. The y position doesn't matter for the y displacement, just the x position matters for the y displacement. And it looks like we've got a -1, which is not nearly as much as the bending displacement this time. Let's think about why. The bending displacement came from the x-directed moment, which is pretty substantial. It's as big as the twisting moment. This is kind of wide in y compared to how it is in x. So should have had not so large of a torsion constant. Torsion constant times g. Let's work out what that is. So how big is JT times g? This will be the thing that we're outputting here right after g. We didn't output g. Sorry, right before theta tip. So it's this thing. So we've got 220,000 for our JTG, and we had 830,000 for our EIY. So it's easier to get a certain amount of twist angle, but the twist angle that we get doesn't actually lead to too much displacement because that gets multiplied by Lx over 2, whereas the bending one got multiplied by a different factor. This was sort of like an Lz along the way, and then an Lx over 2, and the bending one just got multiplied by an Lz squared over 2. And because the length is so much more than the width, torsion is certainly more important than the axial displacement is. So this is much larger than the Poisson displacement, but it's still not quite as much as the bending was. Total displacement then is going to be V tip is V torsion tip plus V, what do we call the other one? V flexure tip plus V Poisson tip. And there we go. So they all ended up moving it in the same direction. Does that make sense? Imagine the tip of this thing. We've got a positive x moment, and that's going to make it bend down. And we have a negative z moment, which makes it twist not in this direction, but in this direction. And that also makes the far top right corner go in the down direction. So from both of those effects together, we have the beam going further in this displacement direction. The last part is going to be to modify some FlexPDE code and calculate this thing using Flex. All right, so as before, we are going to start with the file that we had last time, and this is going to be practice problem 2019 exam Q2. And here, I guess we can change the title. Maybe topic 9, 2019 exam Q2. Yep. So let's put in the dimensions. We've got Lx is 0.05, Ly is 0.1, and Lz is 1. And we have different stresses on that final surface. We have an X stress at the tip. Let's call this SZX of 30E6 times y minus 0.05 over 0.05. We have no Y stress on the tip. And we have a Z stress on the tip, which is 30E6 times X plus Y minus 0.05 over 0.05. Okay, now the Poisson's ratio is 0.3 again, and the Young's modulus is 200 gigapascals. What else do we want to check? We have no weight applied or anything. And we are going to have it fixed on the z equals 0 surface. I've got a fixed boundary condition down here we can copy. And on the top z surface, we are going to say load in U is equal to SZX. Load V is 0. That was the default. We didn't really need to say that one. Load in W is we called this tip. Good. Right. We can't just call it SZX and well, this one we haven't used yet, but we have used SZ already. So we can't have that be this new thing that we're just meaning to be the stress that we apply at the tip there. So once we've done that, we need to make sure the sides of this have no load applied to them. So we'll get rid of that. And we could leave this one there. It's not hurting anything, but let's get rid of that too, just for simplicity. And there we go. We should be drawing the right shape. We just need to report the displacement that we want at this far corner. So let's report V at Lx, Ly, Lz. And why don't we make a contour of U, V, and W on that surface just to see if we can understand why things end up the way they do. On Z equals Lz, Z equals Lz, and yeah. Ooh. What's this? Value of U. I put it in the wrong spot. It's not in the extrusion section. I meant to put this in the boundary condition section a little bit further down. It looks very similar, but this is where you can specify the boundaries for those surfaces. Up here is where you're just drawing the shape. It doesn't happen in the same spot for the extrusion, for that Z surface, like it does for the XY drawing. Okay, so here we have some displacement. It's looking like that far corner. Let's rotate and see if that is indeed the corner we're thinking of. It looks like Y is increasing that way and X is increasing that way. So that means it's sort of this top corner here, and this is going, let's think, due to the twisting of this, twisting in this direction, it is moving in that, it's moving to the right, which is towards more negative Y. And due to the bending kind of down, it also is moving in that Y direction. Which way is Z on this? We got X up and we got Y to the left. So X, Y, X up cross Y is Z out of the page. Z should be out of the page there. Yeah, that makes sense because the close surface of this is the one that's moving. And the Z equals 0 was the one that was fixed. So the shape looks good. What about the displacement? Aha, 1.7 times 10 to the negative 3, pretty close to what we calculated in Maple. So on this surface, we can see how the Y displacement depends on position. It mostly doesn't, which is consistent with the displacement being almost entirely, well, okay, so the bending would have us not change it at all, but what is this difference from here? This is from the torsion. So this change in Y at different positions, giving us a more negative Y, the more positive X we go to, is from the twisting. If we get rid of the torsional moment, the twisting moment, which was the y dependence here, then that should go away and we've got no positional dependence on y anymore. And we end up with 1.5, which is just basically the flexure displacement. Okay, so that dependence on the horizontal position, what the vertical displacement will be, is due to the torsion. That also is what's giving us a vertical dependence on the horizontal displacement on this end. Once again, there's a bit of an offset to that. It's not centered around 0, and that part is because of the flexure. Flexure coming from the x and y dependence of SZ. So specifically the x dependence of that is the one that is giving us a moment about y, which is for bending an x, and the y dependence of that is the one that's giving us a moment about x for bending in y. Just for fun, let's get rid of the torsional moment, and let's get rid of the y dependence on the stress at the tip, the z stress, which should be getting rid of the moment that causes the thing that causes a moment about x and the thing that makes it bend in y. Now we should have almost no displacement in the vertical direction. Very little going on there. We now have something on the order of 1 times 10 to the negative 5, with the thing in the middle being around this 1e minus 5. What about the top corner here? So this top right corner now has a displacement of 1.8 e minus 5. This still isn't quite on the order of the Poisson ratio stuff. We've got 0.1 e minus 5. So we need to turn off the other displacement as well. Oh, we need to put in the average here. So if you just, instead of putting in these values, you put in the average one, which is x is 0.05 over 2, let's say Lx over 2, and Ly over 2. Fix these to that average value, and oh, there, something was going wrong there. We were having just zero, the shear stress was just being equal to this, which was then equal to this. We did like a multi-assignment there. Right. So now we've got a displacement on this thing, which depends on position and should be just from the Poisson's ratio. Yeah. So the displacement is a negative 1.1-ish e minus 6, and that finally is doing the Poisson's ratio displacement. So this now reproduces and agrees with the rest of the calculations we did. We can turn all that back on and get the full thing going in Flex and just kind of enjoy the conclusion of this massive topic. Hope you've had fun. Thanks for watching, and see you next time.